National Science Center of Ukraine, and my co-authors on the theoretical part of this work are Volodymyr and Dubinko. And today I'm going to tell you about extension of the theory of localized anharmonic vibrations and their role in chemical and nuclear physics. In the second part, I will tell you about the experimental verification of this concept, which consists of description of design of a new material enriched with what we think LED sites and of their excitations leading to LED. My collaborations on the nonlinear part are too many to mention, but they are maybe grouped in 7 countries. Together we applied for Horizon 2020 project localized anharmonic vibrations cluster technology, and the outcome is expected this October. So, what are the localized anharmonic vibrations? Can be understood from the very simple model considered by Dubinko 60 years ago almost, when you consider just 2 couple non-linear oscillators. And you give energy or vibrations to one of them. If this energy is large enough, you will be surprised to see that the time of sharing this energy will become infinite, which means that the energy is localized on one of the oscillators. 20 years later, people, mostly mathematicians, understood that in any kind of lattices, 1D, 2D, 3D, modeling the real crystals, we can produce such kind of LEDs, which they are called discrete prisms. If we displace the atoms far enough in order for them to vibrate outside the phonon spectrum. Here, our own molecular dynamic stimulation of discrete preserves in alpha ICCF theorem, made with realistic 3-dimensional potentials. Only 3 rows are highlighted, but the 3-dimensional picture, not a picture or a simulation. And if you displace a few atoms from their positions by fractions of angstroms, then it starts, and for hundreds and hundreds oscillations it proceeds. In more complicated systems, like hydride metals, for instance, there's a large gap in phonon spectrum due to the difference of mass between light and heavy metals. And in this gap, it's possible to excite a discrete prism. Why this is important? Because when you consider the model for any reaction, like a Kramer's model, you need to pass through some barrier, energy barrier. And usually, this barrier is considered to be stationary. But at the site of the LED, it's no longer true, and there's an animation, but I skip it. It starts periodically driving. When you do that, in our paper 5 years ago in Physiograph, we have shown that the rate of transition from one valve to another, that is for the reaction, can be increased by many orders of magnitude. Now the question is how to extend this concept to include quantum effects, tunneling, etc. That can be done if we remind ourselves that only at high temperatures the thermal fluctuations play a decisive role. At low temperatures, 0-point vibrations, quantum effects, are more important. In principle, it's possible to combine both forces in the rate theory concept. And so when we, for instance, heat the system, we increase the temperature. That is, we increase the thermal noise strength. Now the question is, can we increase the quantum noise strength? That is 0-point energy. From the textbooks, we know that for stationary harmonic potential, it's impossible because it's a fixed value. And if you give it energy, you could do it only by steps, and the form of wave function is qualitatively changes. But If you apply this driving like that, then it can be approximated for each of the particles by harmonic potential sitting in one of the wells. And then you will see this problem now can be treated analytically, and in different regions you obtain different results. For instance, in the parametric modulations with the frequency of modulations twice the self-frequency. This case actually will be described in details by the next speaker, Volodymyr. You will see first that the zero-point oscillation energy, amplitude will increase. But what is new, and we showed it for the first time, that its energy also is increased exponentially, not by steps, but monotonously. You are like pumping, like air in the bottle. You are pumping energy in your system. The same is true if you drive the position of an oscillator to enforce. In this case, it starts wandering, and also its energy will be increased. Okay, you cannot tunnel from the harmonic potential, it's infinite. But you can model and numerically solve the problem, Schrödinger equation for double well potential. And then we will see that in the stationary case, for instance, like in this case, if the height is 10 times more than the zero-point energy, you will be sitting almost forever near your computer, and you'll be seeing no evolution. It will ever stay here. This is well-known results, actually. But what is new, that under the driving, just in a 50 to 100 cycles, you will see the appreciable probability of tunneling. How to extend this concept to extreme example of LENR. Why we call it extreme? Why LENR is unbelievable? Because people used to think that the barrier, Coulomb barrier, is huge, 450 kV, which means that the gamma factor probability of tunneling is astronomically small. However, is the Coulomb barrier that huge in the lattice? These questions have been asked by two Nobel laureates, William Lem and Julian Swinger. Lem introduced the electron screening concept for the first time to my knowledge. Now we know, for instance, from Kasaki's experiment, that the maximum that we obtain is 600 eV, which is not enough to compensate for 450K. But Swinger analyzed another cause of screening, lattice screening, which can be understood very easily if you consider deuterons sitting in the adjacent balls, not sitting actually, but oscillating. And this is this zero-point oscillation amplitude introduced by Swinger for this particular problem. And then he showed that you need to integrate. It's not no more the point source of the charge. You need to integrate over the position. Swinger's formula shows that only at large distances you have the usual colonel fraction. At closer distances, its saturates is just 100 eV. That is 3 orders of magnitude less. And then, in another paper in this year, he evaluated the fusion rate between two deuterons, taking into account already all the nuclear parameters of the problem. Yeah? And he defined it like an inverse time of the mean lifetime of the phonon vacuum state. That is, when the nuclear energy is transferred directly to the lattice without radiation of the fast particles. And his estimations for this amplitude of zero-point oscillations, 0.1 angstrom, resulted in these estimations for the fusion rate when the atoms are in one side, in one position of this palladium lattice, or in two adjacent. 10 to minus 30 is too low. Besides, it's a huge increase, but still it's too low to explain observable facts. But now, if we take into account the increase of the amplitude of the oscillations under influence of LENR, periodic driving, then we will see that the height of the barrier in just maybe 20 cycles decreases to just several eV, which means that the problem is reduced to the chemical problem, so to say. And as a result, we have 25 orders of increase in the fusion rate. Now the practical question is where to look for the nuclear active environment. Of course, we need small energy gaps for the LEV formations. And analysis of disordered structures like protein structures results in surprising result that in some topological places the energy is reduced. Another example is small nanoparticles of metal like nickel. This is MD modeling showing that the Dubinko factor, which means a local temperature, atomic temperature, so to say, is different for different atoms and can be higher by order of magnitude along the grades. Also, for instance, palladium cluster saturated with hydrogen shows these strings consisting of 3 atoms, where you can expect something to happen. And finally, in these quasicrystals, there was, for the first time, experimental observations of LIVs in special places. And these LIVs give rise to phasons. Phasons is a shifting of atom from one stable position to another. And the amplitude is increased further from a fraction of angstrom to about 1 angstrom. Okay, now how to make the nuclear active environment? Of course, you need to have a material research group. I'm lucky to have one at my institute. And they can produce a lot of things. For instance, nano-sized particles used to prepare super strong magnets like this neodymium ferroboron. And with, as compared to gas milling, Korea milling results in the real nanoparticles. As a result, the corrosive force can be increased with technological importance. But by my request, they produced by spin melting these strips of neodymium ferro material. Their appearance, their surface is very developed. They all look the same, but their structure is very different when you examine it. It's X-ray. Difference is the degree of crystallinity from 10%, 20 to 45. When we started the first experiment, just saturation and heating in hydrogen atmosphere, we didn't. The result was well, not surprising. The pressure increased a little bit less than it should be without any absorption. But still nothing special happened, and the saturation was less than 1%. But then we changed the apparatus and added electromagnetic driver. And then there was a surprising result. At 300, almost all the gas from the chamber was absorbed. And when you compare the results of the first and the second round, you will see that in the first case, you have the intact the specimens, and the copper foil in which they've been wrapped was undamaged. In the second case, it was a dust, and the foil has been melted. The copper foil, which means that there was heating well above 1000 of Celsius. So of course, it's maybe too early to jump to conclusions, but we may put forward some hypotheses. What is happening? Because only in the second experiment, when we use this electromagnetic driver, they could excite these LEDs, yeah, because they especially prepared only in the amorphous films. Then LEDs may catalyze, and they catalyze as absorption, which we can see. And presumably LENR. LENR produces much heat. Heat melts the structure, which kills LEDs and stops LENR. So the samples cools down in the form of hydride crystals. And this is what we measure after the experiment is done by X-ray analysis. Then what is to be done next? And what is planned to be done? Of course, we need to control the reaction because it's rather difficult to calculate all the energy, and besides, it's too short to jump, let's say. But if we slow down it, then we may, by regulating supply of hydrogen triggering, and then we can measure reduced heat and maybe radiation, and then we can make our conclusions. And now the new installation is under construction, which will be equipped with not only with a heater, but with the electromagnetic driver, we have also electron accelerator at the back here. Yeah, with some energies which can produce also gamma quantas. And in my poster, there's a reason why gammas can be expected, like as a triggers. Yes? And also, there's a gamma detector shielded from the background radiation. So we may conclude that the theory was extended, and based on the theory, a new method of this low temperature catalysis of LENR has been proposed, which is based actually on the excitation of LEDs in the metal halides by two ways, by radiation, which hasn't been checked yet, and by electromagnetic triggering, which shows positive results. And specially designed new materials based on amorphous neodymium ferrum composition. A theory, I think, show abnormal production. So presented results give us evidence to the concept of this dynamite, and new installation is under construction, which is planned to make more results. At least let me thank you for your attention. But for those interested, there's a list of publications, starting with the Physics paper for the concept as such, and another more fresh one, dedicated LENR and LAB bridge in particular. Thank you for your attention.
Thank you, Volodymyr. Are there questions?
I think I understood almost everything, so it's good. In your magnetic, you are using pulsed magnetic fields? What are you using actually?
We are using, yes, they are ferromagnetic. They are ferromagnetic because it's a mixture of neodymium, rare earth material, and metal and ferro.
But I saw a coil on your picture, last picture, you know, the new design you're having. There's a magnetic field. This is, yes, electromagnetic driver.
Yeah. This is a coil, yes, electromagnetic driver, yeah. The idea is to make pulses with different characteristics.
I have a question. Well, somebody else is giving the microphone. In your transfer from the nucleus to the lattice, is this a reversible process or irreversible?
Sorry, which process?
You were talking about transferring energy from the nucleus, nuclear energy, into the lattice. And typically I would look at that as a non-reversible process, an irreversible process. But that presents problems from energy levels that are known. So I was wondering how you thought about that.
Well, in my mind, I agree with you that when the nuclear reaction occurs, that the energy is released, for instance, like in Schwinger's agreement, to the phonons. And this is evidently non-reversible, then it dissipates. So, in any case, this process is not forever, let's say. Yeah? We have some fuel, and when it's spent, it's over. But we have a lot of fuel, for instance.
But the idea is that once you start the decay process, it goes to completion. This sort of, I guess, maybe talking like Peter was talking about the multi-steps going down. Is that, Peter, does that fit your model also, that you're talking many steps going down, but there you're talking about going to specific energy levels that are other nuclear levels? I'll come back. We'll come back to that later. Let's get open other questions.
Thank you, Volodymyr. The specific electromagnetic stimulation, is that calculated on the material used?